So it's another topic to solve a linear differential equation. It is known as the method of variation of parameter. Method of variation of parameter to find pi, particular integral. That means in the previous chapter we just learned the different topic to find different function to find the particular integral. First one is rule 1 e to the power x, second one is rule 2 x to the power m, sin x plus sin x or cos x. Third rule is x to the power m. Fourth rule is e to the power x into v, and the fifth rule is x into v. So many different method we introduced to solve pi in a linear differential equation. Another one is the general method. This general method is also applicable for that, but sometimes it's happened that the right hand side function is too critical, and when we use to find the particular integral using these 6 rules, it's too much difficult to find the solution. In that case we use the method of variation parameter. The question from your side should be, sir, how can I say that this problem is solvable using method of variation of parameter? When it's from your examination related queries, in that case the topic is mentioned that solve this differential equation using method of variation parameter. Otherwise you can use method of variation parameter for those cases whose particular integral is not found by the particular cases. These 5 different cases we have already discussed in the previous lectures. So we start the method of variation of parameter procedure. How can I find the method of variation of parameter? This one you should write very carefully. A more powerful method to find the pi of the equation. That means you can find pi for any linear differential equation with constant coefficient. Okay, so it's a most powerful method, and that was the general form d2y dx2 plus px dy dx plus qx equals to rx. When the general solution of the reduced equation, we have already mentioned, when we consider right hand side equals to 0, that is known as the reduced differential equation. When we consider the general solution of the reduced differential equation, here px and qx need to be a constant. We have already mentioned that linear differential equation, what is essential here to know the complementary function of the equation 1. If it's the variable, in that case you cannot find the complementary function using auxiliary equation norms in advance. Then a particular solution yp of 1 can obtain by this method. It's a lengthy method, so you should recognize or listen very carefully to the procedure working rule. Assume the general solution of 2 is, we just assume this, the general solution of the equation 2, here we mention this one. That means when we find the particular integral for a reduced differential equation, for the reduced differential equation, if we consider c1 c2 are the arbitrary constant and y1x and y2x are the function of x, when we solve this linear differential equation, in that case y1 c1 y1x plus c2 y2x, c1 c2 are the constant and y1 y2 are the two linearly independent solution of 2. Now we shall replace this constant c1 c2 by unknown function v1x and v2x. Since we replace parameter by the function v1x and v2x, so it is known as the method of variation of parameter. We just vary the parameter v1x and v2x. Our problem is to determine v1 and v2. So the particular integral yp should be v1 y1x plus v2 y2x, if we represent it as the equation number 3. Next, to determine v1 v2, we reduce two equation. One is the first to differentiate 1 times dyp, that means when you consider this one is your just here we consider this one is your particular integral. In that case we just differentiate with respect to x of yp. So v1 is a constant. When we differentiate y1x, we just use the norms of u into v. v1 differentiation of y1x is y1 dash. v2 just to ignore the v2, the differentiation of y2x is v2 y2 dash. v1 dash y1 this together with the differentiation of v1 y1, this together v2 y2 dash y2, this together is the differentiation of v2 y2. Why we write in this particular manner? Because we just consider this portion should be 0. Okay, we choose, that is a procedure of the method, we choose this portion should be 0. Here v1 dash y1 plus v2 dash y2 equals to 0. This will reduce 4 to this equation reduced to, if we consider this one is 0, the equation 4 reduced to v1 y1 dash plus v2 y2 dash represent the differentiation. Okay, so move to the next case. Again we differentiate with respect to x of equation 6, then v1 it's become v1 y1 double dash plus v2 y2 double dash, v1 dash y1 dash plus v2 dash y2 dash. Listen it very carefully, v2 dash y2 dash. So here we write this differentiation, v1 y1 double dash plus v2 y2 double dash, v1 double dash y1 plus v2 double dash y2, v2 double dash y2. On substituting 3, 6 and 7 into 1 and rearrange we get, on substituting again we use the term 3, 6 and 7 into 1 and rearrange we get, just observe very carefully, 3, 6 and 7, 3, 6 and 7, 3, 6 and 7. This one is your equation number 3. This one is your equation number 6. This one is your equation number 6. And this one is your equation number 7. On substituting 3, 6 and 7 into 1, we just put in equation 1. What happened? This one is your equation 1. d2y dx2. Just place d2y dx2 here, because this one is your result. Next one is this v1, after substituting this, rearrange we get this result. Here we consider v1 v2 and the remaining term equals to rx. Since y1 y2 are the solution of 2, we just consider y1 y2 are the solution of the equation number 2. y1 y2 is considered as the solution number equation number 2. Therefore y1 y2 should satisfy this equation. That means d2y dy d2y1 dx2 px dy1 dx plus qx equals to 0. Similarly d2y2 dx2 plus px dy2 dx plus qx equals to 0. So this one should be 0, this one should be 0. The remaining portion is v1 dash y1 dash v2 dash y2 dash equals to rx. Sorry, since y1 y2 are the solution of 2, so if we solve for this y2 double dash py1 dash q1 is equals to 0, is equals to 0, this equation reduced to this. Form 8 and 9. Form 8 and 9. Form 8 and 9, when we solve this, v1 dash y1 dash v2 dash y2 dash rx. Solving for v1 v2, here we just mention that should not be 8, that should be your 5. Okay, 5 solving for this one should be solving for this one should be solving for this one should be solving for 5 and 8. This one should be solving for 5 and 8. It should not be 8, that should be 5. Here we write 5 here. Okay, so this one should be the equation number 5. Solving for 5 and 9, solving for 5 and 9, we have this result. Okay, v1 dash and v2 dash. That is your homework. If you face any kind of problem, please feel free to contact with me. When we solve this one, denominator is known as the Wronskian. Denominator is known as the Wronskian y1, y2, y1 dash, y2 dash, which is not equals to 0, which represent y1, y2 are the linearly independent. Okay. Thus, we obtain pi for the solution of 1, namely as this. When we just solve for v1 dash and v2 dash, we get v1 and v2, and put this value of v1 and v2 in this equation, we get the solution of this. In the next lecture, you have some problem. I can understand what's your problem because it's a theoretical expansion. In the next lecture, we will discuss this procedure using a particular example. So happy learning.